Hello and welcome to the Autodidact Scientist's Algorithm series, where I will be giving you an intuitive insight into a variety of different algorithms that are used in machine learning. I'm your host, Regression, and before we get started, I would greatly appreciate if you would like this video and subscribe to the channel. So let's get to it, shall we? And the algorithm we're going to be covering today is linear regression. Now, linear regression is probably the most well-known and well-understood algorithms in statistics and machine learning. So what is linear regression? In the simplest terms, linear regression is a supervised machine learning model that identifies the linear relationship between the dependent variable, which is denoted as y, and the independent variables, which are denoted as x. And it does this by determining the best fit linear line between them. Now, there are two types of linear regression: simple and multi. When there's only one independent variable, simple linear regression is the one that we use to determine its linear connection to the dependent variable. And in contrast, when there's several independent variables, we use the multiple linear regression to identify them relationships. The main goal of linear regression is to find the best fit linear line, the ideal intercept, and the ideal coefficient values so that the error produced is minimized. Now, take a look at the plot that's currently on the screen. X is our independent variable, which is plotted on the x-axis, and Y is the dependent variable, which is plotted on the y-axis. The data points that we can see are the black dots. The slope of the x variable is given by b1, which you can see in green, and the intercept, also in green, b0, is equal to 10 in this particular example. The model's blue line is the regression line, and that is the best fit line, which is, tries to illustrate the linear relationship. Now, if you notice, coming from the black dots, there's a red line, and then they're basically vertical distances between the data point and the regression line, and that is known as the error or the residual. Now, each data point has one particular residual, and the sum of all the differences of them residuals is known as the sum of residuals or the sum of errors. Now, linear regression has a couple of basic assumptions. The first one, pretty obvious: the relationship between your dependent and independent variables needs to be linear. And there's many ways of checking this, but one of the most simple ways to do it is simply plot your dependent variables against your independent variables in a scatter plot, and you'll be able to judge whether the relationship is linear or not. Next one, normality. Both the x and y variables should have a normal distribution. The normal distributions can be checked a number of ways: histograms, KDE plots, and QQ graphs are probably the most popular to do this. Homeoscedasticity. The spread of the residuals or the variance of the error term should be constant for all the values of x. One of the most popular ways to check this is a residual plot. And if you do that, the points on the residual plot will take a shape of a funnel if the assumption is incorrect, or they will remain pretty much constant. There should be no correlation between the variables, which means they should be independent from one another. The way we check this usually is a correlation matrix, but there's a number of other ways, such as VIF, which stands for variance inflation score. The error terms should also be normally distributed. Again, QQ plots, histograms can be used to check that distribution. There should be no autocorrelation, which basically means the error terms should be unrelated to one another as well. The Durbin-Watson test can be used to examine the autocorrelation, which the null hypothesis assumes that autocorrelation does not exist. The test value ranges from about 0 to 4. There's no autocorrelation if the test results is 2. So I suggest, we're going to do a video on the Durban Watson test, but just for reference, I suggest that one is looked up. So there's also a number of ways to deal with violations of these particular set of assumptions. However, this is beyond the scope of this particular session. We will be doing a separate video series into the sort of how to deal with the violations of the assumptions of any particular model. They can get quite complex, so we just literally don't have the time to cover it in this particular video. So how do we evaluate our regression analysis? Now, model evaluation has to be done. It's probably the most important part of a machine learning pipeline. And what I've got on screen at the minute is probably the 4 most common evaluation metrics for regression problems. Now, I'm not going to go too much into the mathematics of each of these. I've put them up there for illustration purposes for those who are mathematically inclined, but we will be creating a video series where we do deep dive on the evaluation metrics for regression classification and whatnot. But for the time being, a deep dive on the mathematics here is a bit out of scope for this particular introductory video. So what we're going to look at first is the R squared, or it's also known as the coefficient of determination. Now, R squared is probably the most employed metric for a model evaluation in regression analysis. It is basically a ratio of variation to total variance, and the R squared output value ranges from 0 to 1, and a value that's closer to 1 indicates a stronger model, the perfect model being shown as number 1. Now, you'll notice in the formula there is an SSRES over SSTOT. Now, that is the residual sum of squares over the total sum of squares, which relates to the error value, which was mentioned earlier in this particular video. So the next one, adjusted R squared. Now, this is an improvement on R squared, because the issue with R squared is that when the number of independent variables increases, so does the value of R, and that prevents producing a meaningful R squared number. So what adjusted R squared does is corrects this flaw. It solely takes into account the attributes that are actually crucial to the particular model, and then can demonstrate how much the model has actually improved in real time. The next one is the mean squared error. Now, this is the mean squared difference between actual values and the predicted values, and the root mean squared error is the standard deviation of the errors or the residuals. The RMSE, as it's known, the root mean squared error, penalizes the large errors, whereas the mean squared error doesn't. Now, this brings us to the end of this particular video on a brief understanding of what linear regression is. So thank you very much for watching. If you have any questions, comments, or feedback regarding the content of this particular video, please reach out to me personally on Twitter or through the Autodidact channels, which you can see we've got a Twitter and a Facebook. And please remember to support us by liking and subscribing to this channel. Thank you very much.